Hi and welcome to another lecture on Calculus 2. Today we are going to talk about trigonometric integrals. Let's go and take a look at the problems we have in mind. So, trigonometric integrals refers to a variety of products of trigonometric functions for which we can give an easy recipe for calculating the integral. We are going to take a look at three types. One is a product of sine and cosine to various powers. Another one, product of secant and tangent to various powers. And the third type is product of these functions but with the argument being a multiple of x as opposed to x itself. So you can have product of a sine of mx and sine of nx, or it can be cosines, or it could be a mix of two functions. So perhaps we are going to start with this one, and then the next one is going to be another short lecture and another short lecture again. Before we get into the details of these integration, let me give a little bit of a motivation why we are trying to do these things and where is this thing going. As far as basic engineering calculations, you are going to be concerned with essentially integral of sine square, integral of cosine square are the most important integrals that you see. That's because of the use in power calculations for electrical circuits and such. Those are quite common. The rest of these things, various powers of sine and cosine or secant tangent, they don't immediately show up in engineering calculations, but some places in advanced engineering or in physics they do. Especially these type of calculations, they do show up in advanced engineering quite often, perhaps under heat transfer and so on. Now, let me give some examples of why we are going after such detailed formulas. One of the basic facts in science you learn is the so-called Newton's law of gravitation. If you have a body of mass m and another one, say, of mass capital M, then the force between these two, if you remember from your science classes, is proportional to the two masses and inversely proportional to the square of the distance. So if this distance is r, if you double this distance, the force is going to drop by a factor of 4. So the force is an attractive force between these two and is one of the main achievements of Isaac Newton. Now a problem comes in the following context. Suppose this one is, say, Earth, which is not a point mass, rather it's a spherical mass. And suppose the other one is the Sun. That one, again, we are going to take it as a spherical mass. And the question is, well, every little piece of this thing is going to tug on every little piece of that one. There is going to be a force between these two. And if you pick another pair of points here, there's going to be a force between these two. And so on. So one major problem, mathematical problem related to physics or wherever you study this thing is, how do I add up all the forces on this sphere? Or how do I add up all the forces on this sphere? Every point of this thing is pulling on every point of that one and vice versa. So it looks like a daunting task. How do I add them up? Well, integration is what does the job of adding little contributions. And when we want to calculate these type of integrals, we come across rather lengthy calculations, and the type of integrations that you do here is going to prepare you for that kind of a work you do later on. Another kind of calculation that you come across perhaps in your circuits classes is a study of magnetic fields created by currents. So if you have a current here going up, say, in the direction of the z-axis, and here is your other coordinate systems. Then you note that there is a magnetic field that is generated around this the wire that's carrying the current. Okay, now suppose the wire that I have in mind is wrapped into a coil, so I can have the wire wrapped perhaps in this style. Let me just draw one circle of this coil. I just have this one. So a current is flowing through this loop. The question is, what kind of a magnetic field are you going to see on the axis of this loop? So every little element of this wire is going to produce a magnetic field all over the space. If you are focusing on points on the axis, there is going to be some magnetic field here. And then if you look at another little piece of this wire, that's going to create another little magnetic contribution. Every little piece of this thing creates a small piece of this puzzle, and they are going to be all these little magnetic fields created by different elements of this wire. And the question, well, what's the net magnetic field at this location? I have to add up all these contributions to figure out what the total is going to be. And of course, the typical coil has many of these loops going all over the place. How do I add them up? Again, the process of calculation of such things is going to require some rather tricky integrals, and the kind of problems we look at here prepares you for that kind of tough problems in the future. So the kind of work that you are going to do here is going to be a little bit more detailed than what you're used to from Calculus 1, but it's quite doable. So let's go focus on the first types, product of powers of sine and cosine. So it all depends on what kind of powers do you have. Being odd or even is going to make a difference for us. If some of them are fractional powers or negative powers, that's going to be a different kind of situation to look at. Let's start by the easiest case. Suppose so we are going to take a look at problems of type sine to some power of x, cosine to some other power of x, dx. So let's do a few examples so that we see various considerations that are important here. One is, if one of your exponents is an odd number, one exponent is an odd number. Sometimes maybe you have both of them are odd numbers. In that case, if you have both of them are odd numbers, if you have a choice, pick the smaller odd number. If you have a choice, focus on the smaller one, just so that our job is easier. Let's just write an example. Suppose I have, say, sine to power of 11 of x, and then say, let's make this one smaller, cosine to power of 5 of x dx. I want to calculate this. Well, we remember derivative of sine is cosine, derivative of cosine is negative sine, and so on. So what I'm going to do is to convert as much of this possible to sine and leave one cosine out. Why do we do that? Because when we want to do a substitution of u being sine of x, the derivative of that u is going to be cosine of x. Let's see how does this work. First of all, remember the basic trig identity. Cosine squared plus sine squared is equal to 1. So for example, if you want to isolate cosine square of x, of course you can replace it by 1 minus sine square of x. So what I have here is therefore sine to power of 11 of x. I separate an even exponent of this, and then when single cosine out, then this cosine is going to be written as 1 minus sine square of x. That's for cosine squared. This is cosine to power of 4, so I need to square this. Then cosine of x dx. To make our writing a little bit less lengthy, let's introduce our substitution already. So I take u to be sine of x, and therefore of course du is going to be cosine of x dx. So it's nice that I already see my du here. This is my du. Let's write the rest of it. Sine, we said we are going to call it u. This was 1 minus u squared, and this is du. Okay, now we see the light at the end of the tunnel, because I can open this thing, multiply, and I have just a polynomial integration, and that's the easiest type. So I have u to power of 11, 1 minus 2u squared plus u4 du, and from here on is just downhill. Is that right? So let's make sure everybody participates. Quickly tell me in a matter of a couple of seconds what the integral will be. So of course we are going to have u to power of 11 minus 2u power of 13 plus u to power of 15 du, and antiderivative is going to be u12 minus 2u14 over 14 plus u16 over 16, and a constant, and then we do back substitution. So this has to be sine 12 minus 2 sine 14 plus sine 16 and a constant. So quite interesting problem. Starting with this, we end up with an expression of this type. Let's go back, see what makes it to be relatively easy compared to the problems that come up. The fact that this was odd, so I could separate a single one with an even one. Even, by the trigonometric identity, we can convert it to sine, and once that conversion is done, all we are looking at is a polynomial integration, and that is relatively easy. So let me ask you to do the following. Say sine to power of 13 of x, cosine to power of let's keep it small again, 5x dx. Here's another example. What about the other way? Suppose I had cosine to power of 17 of x, sine to power of 5 of x dx. So you do these two problems. We are going to move on to another example. It's possible that one of the powers is not what we are used to. It could be a fractional power and such. So here's another example then. So I could have something like integral of cosine to power of 5 of x, and then sine to power of, let's say, 1/3 of x dx. Again, the fact that this is odd is going to rescue us. We have no choice about that one. So the fact that this is denominator is odd is of no relevance. We have to take this one and split it so that we can use make use of this Pythagorean identity. So how does this proceed? So I separate one cosine, so cosine of x dx, I keep that for my differential. I'll have cosine to power of 4x, and then sine to power of 1/3 x, and again I introduce my u to be cosine of x. Excuse me, of course I need to u to be sine of x. Why? So that it's du becomes cosine of x dx. Make the substitution here. So cosine squared will be 1 minus sine squared, but cosine to power of 4 is going to be square of that, then times whatever power I have here. And this is cosine of x dx. So now I go ahead and make my substitution. This becomes 1 minus u squared squared. This is u to power of 1/3, and this all of that becomes du. So now I can open this thing, becomes 1 minus 2u squared plus u4 to power of times u to power of 1/3 du. From here on it's going to be downhill, is that right? You multiply, and it's essentially polynomial integration. U to power of 1/3 minus 2u to power of 2 and 1/3 makes 7/3, and then 4 and 1/3 becomes 13/3 du. So I integrate, so u to power of this is 4/3 over 4/3 minus 2u to power of this is 10/3, adding 1 to that, dividing by 10/3 plus u to power of this is going up by 1, becomes 16/3, and then 16/3, and then a constant, and then we go back and do the back substitution. Our u is sine of x, so cleaning up these fractions, this is 3/4 of sine of x to power of 4/3. This becomes 6/10 of sine of x to power of 10/3, and then this becomes 3/16 of sine of x to power of 16/3, and then you throw in a constant for good measure. So that's another example of this. So in all of these cases, what rescued the situation is that one of the powers was odd. If you were lucky that both of them are odd, we said we go with a smaller one. Well, what does that leave out? Leave out the case, what if they were both even? What are we going to do in that case? Well, this is actually going to bring us to that most important integral of this whole category for basic engineering calculation, which is what is the integral of cosine square of x dx, or what's the integral of sine square of x dx. Why are these two integrals are so important? Because the powers in alternating current are proportional to this kind of entities, and the integral of a power over time is the amount of energy you're consuming. So this type of integrals are very basic about power consumption in alternating current situations. So what are they doing in our situation? What is important is that their exponents are even. In this category, if you want to make the problem lengthier as far as the algebra are concerned, for example, you could talk about something like this. This fits in this category as well, even though I'm going to leave it to you because the algebra is a little bit lengthy, and that's not the purpose of what we're trying to do here. So common thing about all of these problems, is these three problems, is that the exponent is even. If we are going to try what we did before in these type of problems, you see that we are going to make the problem worse because we cannot make easy use of the Pythagorean identity, because the power after you leave one out, what is left is odd, and then we end up having these things inside of a radical, and that's not the good news. That makes the problem a lot harder. So what is the approach here? The approach is a very basic, very important formula you know from your trigonometry classes, and that's a so-called double angle formula. Okay, double angle formulas, you remember that cosine of 2x has three reincarnation from that trigonometric classes. One of them is cosine square of x minus sine square of x. Another version of this is that this is 2 cosine square of x minus 1. A third version of this is that it's 1 minus 2 sine square of x. Okay, so go back to your trig text or appendix in your calculus text. You will see a treasure trove of trig formulas. The one that we are using here listed under double angle. Okay, we are going to concentrate on the second and third one of these things. What we get from the second one is cosine square of x. I take the 1 to the other side, so it becomes 1 plus cosine of 2x over 2. And here I do the same thing. I get sine square of x, taking this to that side and this to the right side, becomes 1 minus cosine of 2x over 2. Sometimes they might be referring to these things as a half angle formula. This is really the same thing. It all depends on your point of view. Okay, what does that have to do with us? What it has to do with us is that I can take these functions and replace them by this double angle, and once I do that, I'm getting rid of the power. The power is taken off. In exchange, we have a multiple of x in the argument of the function. Well, as far as the integration is concerned, this is a lot friendlier than that one, and we are essentially got it made. So let's do the following example. Suppose I want to figure out cosine to power of, well, let's do the cosine square itself first. Cosine square of x dx. Well, the trick is just to replace it by that. 1 plus cosine of 2x over 2. Put the factor of a half outside. Integrate antiderivative of 1. What's the antiderivative of 1? Huh? Everybody, do you have that answer for me in a matter of second? Antiderivative of 1. What's that? Well, that's just x. How about cosine? What's the antiderivative of cosine of 2x? Well, of course, that is sine of 2x, but I have to divide by 2. And then you can throw in a constant. If you want to get rid of the parentheses, it's going to be 1/2. This is 1/2 of x over 2, plus sine of 2x over 4, and then a constant. What if I had higher powers but still even? Well, I have to work a bit harder, because now I write this thing as cosine square of x squared. Cosine squared, just like here, I will replace it by 1 plus cosine of 2x over 2 squared. Now I open this thing, so we are not doing any integral, we are just doing trig substitutions, trig replacements, and then just the algebra. So square of a half, let me put this outside, and then 1 plus cosine squared, 1 plus twice the first times the second, 2 cosine of 2x, and then here's a trouble spot. Again, I have to square my last item. Okay, we cured a little bit. We went from 4 to power 2, but again, I can't handle 2 power directly. I have to apply another power reduction formula. So sometimes these formulas are called power reduction. This is 1/4 of integral of the first one is 1 plus 2 cosine of x. that is easy for me. Let me write all of it at the same place first, and then we separate them later. 1 plus 2 cosine of x, 2x, and this is going to be 1 plus cosine of, now I have to double this angle, so it becomes 4x divided by 2 dx. Let's clean up. So I have 1/4, 1 and 1/2. I can write it as 3/2. This is 2 cosine of 2x, and this is 1/2 of cosine of 4x, then dx. I have to put this in a parentheses. Now if you want to make it look nice, maybe you want to separate it or take a common denominator, or however you want to do. So let's write this 1/4. Antiderivative of this one is 3/2 of x. 1/4 times 2 times antiderivative of this is sine of 2x over 2, and then 1/4 times half is 1/8. Antiderivative of this thing is going to be sine of 4x over 4, and then a constant. Then of course you can simplify it a little bit, and then you'll have your antiderivative. Okay, so you notice the amount of work is expanding, and as a character or nature of the beast is like that. So as you go to higher and higher power, in this case you have more and more work to do, but I think we can postpone that to some other time. So we looked at a variety of cases right now. Powers of sine and cosine, variety of types were considered. Let's do the secant tangent and these type of products in a subsequent lecture. Again, I realize it's going to be rather detailed work, but it's a practice on integration. The ideas that you learned in calculus 1, they are going to settle in your mind, and also things you learned from trigonometry, they are being taken out of the cupboard again. We are taking a look at them and making sure that we actually still remember them. Okay, until next lecture, good luck and God bless.